Let's consider a round torsion bar of length L, and it's subjected to two torques. T1 is located at distance A from the left-hand side, which is built into a wall, and on the right-hand side I have a point torque T2. We'll go ahead and assume that Gj is a constant, and let's ask ourselves the question of finding what the internal torque field looks like, what the twist rate field looks like, what the shear strain field looks like, and what the shear stress field looks like. So basically we're going to ask ourselves the question of what's the complete mechanical response of the system here. So we'll go ahead and we'll start with a free body diagram. So I'll draw a free body diagram of the whole bar. So there's going to be a reaction torque on the left-hand side here. So I'll call that TR for reaction. And then there's the two applied torques, T1 and T2. So if I sum the moments about the z-axis, I'm going to find out that the reaction torque is equal to T1 plus T2. So, and now if I can go ahead and draw my internal torque diagram. Let me first make a section cut between the wall and T1. If I do that, I'll have this free body diagram here, which tells me that the internal torque between the left wall and torque 1 is going to be T1 plus T2 always. If I make a section cut on the other side of T1, I'll have this free body diagram here. And if I sum the forces in the or the moments about the z-axis, I'm going to find out that T of z is equal to TR minus T1, which happens to be equal then to T2. So I can quickly sketch that up. So I have T as a function of z. It's a stepwise function. It's T1 plus T2 out to A. And then from A to L, it takes on a value of T2. Knowing that, I can quickly draw a graph of the twist rate, because the twist rate is going to be the torque divided by Gj. So I'll have a stepwise function, looks exactly the same, it's just that the values are now going to be the torques that I had before divided by Gj. Knowing the twist rate, I know what the shear strains are. The shear strains are always R times the twist rate. I have R times T1 plus T2 over Gj for values of z less than A. And I have R times T2 over Gj for values of z greater than A. At A I have a jump, so I don't really know what's happening there. If I want the shear stress, I'm going to go ahead and multiply those values of the shear strain by G. So I'm going to get R times T1 plus T2 over J for small values of z, and for values of z greater than A, I'll have R times T2 over J. If I want, I could also answer the question of what the rotation field looks like by simply integrating the twist rate. And so if I do that, I'll find that I have this graph that looks like this. It's linear from 0 to A, and the slope of that line is going to be the twist rate over that region, which is T1 plus T2 over Gj. And then from A to L, I'll have a straight line whose slope is T2 over Gj.